Okay, welcome. Welcome to our second talk. This time we have Alejandro Jofre from CNRS, Centro de Mathematic Modeling, Centro de Modelamiento Matemático, Center for Mathematical Modeling. This is a UMI in Chile. He will speak of games, Nash equilibrium in energy markets and with networks. Please.
Well, I changed a little the title and the talk because I think it's more representative of what we are doing in our center. I realized only yesterday that I was always saying that CMM was the first UMI in mathematics, but I think this is the first UMI. Consider all the subjects. So it was created in 2000. So, well, it's just discovered only yesterday. So, okay, we are very proud to be one of the first, and the first. We are the first UMI. So in this UMI, during the last 15 years, we have been developing mathematics but in many cases connected or motivated by some specific applications or issues coming from the industry, but sometimes also coming from the public policy, not only industry, but also connect with issues on like regulation of markets or in telecommunication, in energy, in water supply, gas supply. So it's been always a mix of industry, private sector, but also public sector. So today is what we're going to explain is one example of this interaction between mathematics and in this case is the analysis of the behavior of agents interacting in electricity markets. Okay, so let me explain. Let me first motivate, and then I go into the mathematics later. In this kind of market, there are, in general, few agents. When I say few agents, few owners of energy productions. For example, in many countries, the owners of the whole system are less than 10. In Chile, there are 4. In many countries, actually, are less than 5. The big owner of the energy system. I know that Mexico now is moving to privatization of the system, energy market. Okay, and no, okay. But even if you do that, and then in Chile and UK were the first in 1981. Then now, and after more than 30 years, the concentration of the ownership of the markets is in few actors, less than 10. And then it means that we are far from what is called in economics perfect market. Okay, and then what we really require is to study which is called an oligopoly market. Or oligopoly means few actors, few agents, few owners that can control or try to manipulate the prices and supply and so on. Then this is the framework that I'm going to develop using more sophisticated mathematics. I am far from the perfect market. We have few actors, and think about maybe 5. Then this is why I call oligopoly theory. Second component, which is also relevant in this kind of model, is a network, and it's also something which is not considered in general in the market from the economic point of view. if I am here and then I am demanding electricity and the supply is far, the plant supplying electricity is far, then I need to send electricity from this very far to here. Then it's clear that it's not the same as the generation plant is very close, because there are losses of energy when you send energy from one far point to here, and then the topology of the network is important, because if you are far and there is only one supplier, then this supply is going to take a maximum of rent, maximum of they have whole control of the price and everything. So you have the topology of the network, transmission network, is more dense in the sense that they cover between demand and supply, cover more or less the country. Then there are less opportunity to have a monopoly behavior. Okay, so this is and this is true and especially true when you have highly congested transmission line. You have a network connecting supply and demand, and then you have a highly congested line. So this congestion is going to induce monopoly behavior. This is one of the second thing that we are going to show. Okay, this idea of the control of prices in economics is called market power. It's a power to control or to manipulate prices, market power. So there is a famous paper called Market Power in Power Market. Okay. Okay. So this is an example of in Europe of the transmission network. When I say transmission network, I mean high voltage of transmission, the big line of connecting supply and demand, like I have here in this picture. The same is true. Another example, California system. Then at each node you have a supplier or demand. And then, for example, different node mean different technology. You have a gas supply on a hydro energy or combined cycle on a coal, nuclear, so on. Okay. Then at each node you have different suppliers, and then you have different, and also you could have a demand node. So this is the graph. An example. Another example is this is a Brazilian. I don't have a picture of the Mexican transmission system, but here again is very dense in the density of the graph. The connection depends on the demand. For example, here, São Paulo, Rio de Janeiro is more dense than the other part. Here, it's only the Brazilian is an interesting system because it's very dense here. It's very dense in the north, and then this one few lines connecting north and south. The same is true in the case of Chile, it's a very long country, and almost one-dimensional country, and then is of course the intent of the topology of the network is very simple, and then we pay a lot of attention to this monopoly behavior. New Zealand is another good example because New Zealand have the North Island, the South Island, and only a couple of lines connecting north and south. Okay. So, well, two more pieces of information before going to model. This is the cost, the shape of the cost function for an owner that have different technology. You see, which is something very important, that we have this, well, first increasing, this is an increasing curve because more generation is more expensive because you need capacity investment, increasing, and convex. And the convexity is going to be a key point in all this model we are going to develop. Like in the previous talk, convexity, C convexity was important. Here, the convexity is going to be very important. You will see from the mathematical point of view, from the numerical point of view, from the behavior point of view. And this is an important point. Cost curves are convex. And the second point is this. This is real data. This picture is real data. And the second point is also real data. Prices, if you look prices in different locations, can be really different because this network effect. So this picture is showing, I'm showing the different location, and for different locations you have different prices. Okay, for example, this corresponds to New York. Then New York, the blue one, the red one is the New York. See, you see here, for example, at 7 p.m., which is a peak in the demand, you have different, very different prices in different locations. So and then this is an important point because, well, somebody who lives here in Cuernavaca should pay different prices for electricity compared to somebody who living in other city. Okay, well, the answer is, well, we say no. It should be the access to energy should be the same. But then how to deal with this? And then my point is, it's better to compute first the real price, the cost, and then to redistribute later to have uniform prices per region or per country. But it's better to know exactly what is the cost, because then you can subsidize or you can do other policy. But it's better, and then this is my our proposal concerning prices. Then we have and today we have the technology from the mathematical point of view and from the numerical point of view to compute prices in different locations, and then to have a clear idea of how the costs are in different places. Okay. Well, then let me go to the model. How this model works in general. Today, I'm going to explain the model in one very example. They had one day ahead market. In today the generators will then send the cost function to produce electricity for tomorrow. These cost functions are this convex. So the variable of the company are these increasing convex functions. This is a variable. It's an infinite dimensional space. It's a space of convex increasing functions. Okay, this is the variable for the generators. So the generators sent to one regulator, or here is called independent system operator, ISO. Then today they send this cost curve, repeat, increasing convex, and then the regulator, the ISO, takes this information and then solve a problem to an optimization problem corresponding to. I'm going to put here. This is these are these convex functions sent by the generators. And the regulator is going to take the sum, it's going to minimize the sum of the total cost, subject to three kind of constraints. One is supply, this is correspond to the supply, and then this is the demand. And these are the, I'm going to explain in a few moments. And then these are the capacity, because each generator has a maximum capacity for generations, and this is capacity of transmission lines. So this is the regulator is responsible for the benefit for the society, in the sense that the regulator is going to minimize the total cost. It's going to take the cheapest way to generate, because we're minimizing the sum of the cost, subject to supply and demand should be satisfied at any point in this graph that I just show you, because and I want everybody should have the demand, okay, and then this is supply. Supply is coming from, if I am at the node I, this is the generation at node I, plus all the energy sent coming from other nodes, and this corresponds to the sum of this H are the flows coming from different node to node I, and this is the supply part, and the demand part is the demand at the node I. As you have Cuernavaca is the demand of Cuernavaca, plus this term is nonlinear, corresponding to the losses. The losses, when you say electricity from one point to another, the losses depend quadratically on the flows. But then this is a convex problem, because this supply, this quadratic term is in the left side of the inequality, so it's convex. These functions are convex. Then the whole problem is convex, which is very important. And then this ISO solved this big, there's a huge optimization problem. This is thousands of variables and flows and nodes. You see, for example, in the case of California, and there are thousands of Europe, and there are thousands of nodes and arcs and connecting nodes and demand and supply. So here, the regulator is going to take solve this problem. Is going to take two information. First, the optimal QI, which corresponds to how much each generator is going to produce. And I repeat again, is going to, because of this optimization problem, is going to be always the cheapest first, and then the second cheapest, and so on. Okay. And then the second part of information is the lambda, which corresponds to the multiplier. This is associated to the dual problem, the multiplier associated to this supply and demand constraint. There are two, and why it is important, the multiplier? Because the multiplier is going to be used for computed the profit for each generator. Because remember, the regulator is going to minimize the total cost, but the generators, the company, are going to maximize profit. So how they compute the profit is multipliers coming from the previous problem, from the supply and demand constraint, times the quantity produced minus the real cost. And then I make the difference between here the real cost and the cost function submitted, bidded. There is a difference between, and this is real, and we have real data for that. There is this kind of market allows that the cost bidded could be different compared with the real cost. Okay, because if the generator bid or sent to the regulator the real cost, then the profit is zero. But just because we are not in the perfect market, we are in the oligopoly framework. We showed that in one of the results later that there is always a difference between real cost and the cost bidded, even at equilibrium. So then, what is the strategy for what is the strategy for the generator? Well, as I said before, are these convex functions. These convex functions are the barrier for the only thing they can do is to bid different cost functions, convex. So the space of strategy is this space of convex on decreasing with a slow bounded, and then this is a space we work on in this problem. So let's go to now okay, it's half an hour. So then in this setting, well, you see here, let me come back a few seconds to the, well, you see here that the optimal solution, Qi, and the multiplier depend on the Ci. Not only one Ci, all the Ci's, okay? It means that the optimal solution and the lambda multiplier are going to depend on all the costs bid by a different company. It means that and the company are maximizing, this minimizing. It means that we are in the framework of a game because there is a conflict between minimizing the total cost and the strategy for the players or the generators, CIs. So this is why in this market, what we, according to the definition and the way they are defined in this market, what we are looking for is a Nash equilibrium on on this game, and then the payoff for the this is the payoff for the generators. This the multiplier time quantity minus the real cost, and the other. These are, imagine that we have 5 owners of this whole system. Then five agents are maximizing, and 1 agent, the regulator, is minimizing. This is the conflict. Okay, so one of the then that now becomes the mathematical difficulty. Well, there is a very famous Nash existence result, right? But the Nash requires some continuity and convexity and compactness. First, the Nash theorem requires the convexity and compactness of the strategy. But here is not a problem because the space of convex non-decreasing functions, convex lower semi-continuous because is a convex first. Convex combination of these functions is convex. It's going to be bounded because we are asking that the slope of this cost curve are bounded, and also then it's convex and it's going to be compact because of this uniformly bounded slopes. Remember, it's very natural to assume that there is a cost which is a slope. It's a slope. We cannot. We don't have in this case infinite slope because infinite slope means infinite cost. Okay, and we can always say that there is a cost dominating all the costs of the different technologies. So it's a natural assumption. So we have convexity and we have compactness of the strategy, but then the difficulty comes from the continuity property because these functions, when you look at this function as a function of C, first are not convex or concave because they are maximizing, are not concave first, but more serious are discontinuous in a very bad way, in the sense that if you remember, I will go to the, let me jump to the classical result of Nash, existing Nash, just for, oops. Yeah. So this is a Nash, classical Nash result for existence of an equilibrium. In the UI are the functions, payoff functions. Then the classical Nash require the upper semi-continuity with respect to both variables, and the lower semi-continuity with respect to the variable of the competitor. Remember that xi, the strategy set for us is the convex non-decreasing functions in the infinite dimensional space. Then we have this upper semi-continuity condition and the lower semi-continuity condition, and then we have the Nash equilibrium, the existence of a Nash equilibrium. This is a classical Nash, and then but the problem for in our case is that we have discontinuities. Just want to make pictures of the. Okay. Yeah, I'm going to use only one. I want to make only one picture. If you look at the function, this profit function, multiplier time quantity Q minus the real cost, these functions are non-convex, but then you have this kind of picture. And then what happens when two generators you have two different curves. This is generator 1, for example, and generator 2 is like this. But at some point, you have the same price. Okay? Then what is the usual rule when you have the same price? Then the usual rule in this kind of market is the delta excess of demand is divided half and half, which is, well, because, well, if the two are the same price, have the same price, same cost, then half for you, half for, or any combination of this. And then this kind of tie-breaking rule, this kind of half, produce this kind of function. This with jump, because you are generating, and then suddenly you have less because you're going to share the delta with the other generator with the same cost. So you have a jump, and then this is kind of jump, and the value is something between. The profit then have this kind of behavior. So when you have this kind of discontinuity, then the function is not lower and is not lower, not upper semi-continuous. You don't have upper semi-continuity, you don't have lower semi-continuity when you have the jump with something between. So what we can do? Then you want to prove existence. We know that this kind of function is very natural in these games. So what there is a famous theorem, an extension of the Nash, classical Nash result, proved by Rennie in 1999 in an econometric paper. He proved that with this condition, I'm going to explain the condition, we have the existence even in the case where we have this kind of jump. But then later, we in our paper in 2006, we extended the result just for this kind of situation when you have these jumps, and then this condition, which is called battery price secure, is very easy to explain. I'm not go into detail exactly what are the conditions, because one way to explain is the following. And if you want to have the existence of a Nash equilibrium in the case of discontinuities, including this kind of discontinuities with jumps, something in between, then we have existence if we have the following behavior. If you have all the agents jump up and at least one jump down, then it's okay. Then the bad situation is when everybody jump up or jump down at the same time. But here, if one of them jump in the opposite direction, it's not important the magnitude of the jump, only the sign of the jump. If then you have jumps in, everybody jump, then in the opposite direction, it's okay. And this is the case. It's just the case for electricity market, because in the electricity market, when you, if you indicate this half rule, if you give some demand to one player, the other one will going to be less. Okay, so this jump up, jump down is very natural in this kind of market. So what we use this result that we proved in 2006, and this for this in this situation where you have a few agents and the payoff this kind of payoff with multipliers and optimal solution coming from an optimization problem with jumps in a very natural way. So this is the result, but I'm going to skip this. And then this is the existing result. So if you have a space of strategy which is close with this pointwise convergence, which is the case because for convex, it's also very nice in convexity. Pointwise convergence on uniform convergence is the same for this non-decreasing convex functions. So we are lucky in that sense, and then we are able to prove the existence of a Nash equilibrium in this case. But and then we proved the existence, but when a couple of years ago, when we proved the existence, we realized that something really bad of this equilibrium. And let me explain what is really bad. What is really bad is I'm going to explain in the very simple case of two nodes and one line. Which is really bad for this equilibrium is that the equilibrium produces prices which are always strictly greater than real cost. Always. Even in this case, you have two nodes, one arc connecting these two nodes. Imagine that you have a demand here, demand there, one generator here, one generator there. And then if you compute the Nash for this, in this case, then the result is the real cost. Here. The result, the Nash equilibrium, is the real cost divided by this 1 minus 2 RD. Then R is the resistance of the line. So if the R is 0, then the Nash coincides with the real cost. This is the perfect market situation. But if there are losses, then there is some resistance in the line, which is the real case. And then the Nash is always, because this quantity is less than 1, then the Nash is always strictly greater than the real cost. So then, I am saying that the market are built in the way that the equilibrium is give prices is strictly greater than the real cost. If you have a network, and then this is why I said at the beginning that the network is important. It's important to consider the network because the network is something real. We have transmission lines, we have losses, and everything. Everything is true. So then the point is why is this Nash why this difference is produced? And the reason is because in this kind of market, the generator are able to bid to send to your regulator something different than the real cost, right? But then there is nothing to do. Then in the sense that there is this asymmetric information between the regulator and the companies. The company, in order to get to know the real cost for electricity companies is really very hard because they have different contracts. Imagine a company producing electricity using gas. Yes. So while the contracts are completely different, the contracts are very difficult to have access to the gas supply, so very complex. So then I finish. Then the message is if you want to then this kind of market produce this game with discontinuity. It's possible to solve the discontinuity using new result for Nash system. And the equilibrium produces prices higher than the real cost. And there are some ways to avoid this, but that require the use of economic model considering asymmetric information. But this is we also work on that. We have a couple of papers on that, but this is for another talk. Thank you very much.
time for a question. Yes. Question.
Yeah.
So the must jump up, must jump down fact that enabled you to prove the hypothesis in the earlier result.
Yeah.
Is that because when electricity is produced, it has to be spent?
Yes.
So if you added storage to the market, say you had batteries, so that you could potentially choose to store,
Yes.
which now is, I think, really important because of all of the renewable energy and the need for storage. Does that change that assumption?
Well, no, you still have jumps, but the battery will smooth in some way the behavior, but or still with jumps. But the problem is that it depends on if the battery is public information or private information. If the capacity of storage is private information, you have the same problem. If it is public information, like for example, if you keep your energy in a reservoirs, then these reservoirs are more or less public information. So that is better.
I have one other question. The Nash difference between C bar seems to suggest, maybe I'm wrong, that the energy producers make more money if resistance is higher.
Yes.
So there's a perverse force that they should have more resistive.
Exactly. There is a perverse behavior to invest less on transmission. This is why it's so important to have a separate company in one side generator, in another side transmission. And you see in the market around the world have been separated. And I don't know, in Mexico maybe still one company. I don't know, in many countries now are a separate company because it's a perverse. Yeah. Yeah.
This existence result that you have.
Yes.
Have you proved that it is unique? The equilibrium?
No. Usually there are several equilibrium points, but because the fact that we have this regulator minimizing cost, this regulator is going to choose the best for the best of equilibrium. The best in the sense that minimizing the total cost of the system. Yeah. Yeah, I forgot to say that from a mathematical point of view, it's interesting because you know that Nash equilibrium is based on Brouwer fixed point, and that it requires continuity. But here is a result without continuity. So it's something. Well, the proof of this is based on the approximation is an approximation of this continuous function by continuous function, and then at the limit everything works well. This is the basic idea behind the proof, but it's an extension also of the fixed point for discontinuous functions.
Thank you very much. Thank you again, the speaker.